In this video, we will continue to look at Poisson approximation. So recall that in the previous video, we saw that Poisson distribution can be used to approximate binomial distribution even when the trials are not independent but weakly dependent. In this video, we look at another variation of that. So what we are going to look at is that again we are going to look at a situation where we have n trials and the trials may be independent or may be weakly dependent, and each trial will have two outcomes, success or failure. However, this time the probability of success will not be the same for each trial. So let me describe the situation. So to consider n events, e1, e2, en, and define n trials in the following way. The ith trial for each I, for I between 1 and for I between 1 and n, the ith trial has two outcomes, success or failure. Success means that the event EI occurs, and failure means that the event EI doesn't occur. And the probability of success here is the same as the probability of EI, is given by PI. So that is, here we are assuming that the probability of success may not be the same for each trial. So the probability of success in the first trial is P1, probability of success in the second trial is P2, and so on. Once again, let x be the number of successes. So that means, if you think about what success means, the number of successes means here the number of the events E1 to En that occur, the number of these events that occur. Okay, so here we're going to assume that the events E1, E2, En are independent or weakly dependent. Now let's ask ourselves what would be the expectation of x. So first of all, let's say we want to find the expectation of x, and in order to do that, what I'm going to do is I'm going to define n random variables in the following way. So x subscript ei is a random variable, and the value of the random variable is 1 if the event ei occurs, and it will be 0 else. And this is for each I 1 to ... n. Then notice notice that the variable x, which is the number of number of these events that occur. So x is equal to x ei plus x, not ei, sorry, x e1 plus x e2 plus dot 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 plus x en. And we're going to use the summation notation here, so this will be I from 1 to n x ei. And so once we see that this equation holds, then we can say that the expectation of x will be the summation I going from 1 up to n, the expectation of xei. And clearly, what is the expectation of xei? Well, this is the summation I going from 1 up to n, and the expectation of xei is the same as 1 times the probability that the variable xei is 1 plus 0 times the probability that the variable xei is 0. Clearly this is equal to the summation I going from 1 up to n, the probability that the variable xei is 1. Now remember, by definition xei is 1 whenever ei occurs, right? So that means the probability is the same as the probability that ei occurs. So this is the probability that ei occurs, which, remember, we said we denoted by pi. So this would be I going from 1 up to n pi. So let's recall that we denoted by pi the probability of ei. So the expectation of the random variable x, which is the number of these n events that occur, and the expectation is the summation of, so let me write a final equation here. The expectation of x is the summation of pi I going from 1 to n. What I'm going to do now is I'm going to define or let lambda to be the expectation of x, which is the summation of pi, and what I'm going to claim now is that the distribution of x is approximately a Poisson distribution with the parameter lambda approximately. When n is large. And you also want the pi's to be small. So this probabilities here, you want them to be small. Okay, so let's do an example. let's say we flip n coins with the probability of head being p1 ... pn respectively. So you have the probability of getting a head on the first coin is p1, the probability of getting a head on the second coin is p2, and so on. Let x be the number of heads, then this situation is exactly the same situation as we have described here. Here the events are so in my example, E1 is the event of getting a head from the first coin. E2 is the event of getting a head from the second coin flip. En is the event of getting a head on the nth coin flip. So by what we discussed before, then x will have Poisson distribution with parameter lambda, which is the sum of the probabilities pi, and this is, of course, I want to emphasize, is approximately. Okay, so I'm going to end this video right here. In the next video we will discuss further on the application of the Poisson distribution.